Hey, so this is Joe, and this is the second video of the 7th chapter of Stewart's Calculus, and we're going to be doing another integration technique, and that is trigonometric substitutions. And so, in order to do these substitutions, we're going to have to use a couple new integration formula later on down the line when we solve these problems. So here they are. So the integral of tangent x is going to be the natural log of the absolute value of secant x plus c. The integral of secant x is going to be the natural log of secant x plus tangent x plus c. And then we've got kind of the same rule for numbers 3 and 4. When we have the we add a negative. And then all the other trig functions have the on them too, and otherwise, in terms of like the broad framework of the formula, they're the same as 1 and 2. Also, your book has the proofs for these, so I'm not going to do them right here. You can look in your book. They have a really great kind of outline for that. Also, in order to do trig substitutions, we need to know some properties of trig functions, and your book kind of goes over them, but also if you're having trouble with that, I recommend you watch some of our pre-calc videos, and they will clear that up for you really well. So, unlike integration by parts that has a really nice sort of formula and proof for the formula, trig substitutions don't really have that. It's just another kind of substitution, similar to a U substitution, but a little bit different. I mean, it's a different method, so yeah, it's a little bit different. So I'm just going to do a couple problems and show you the method, and then I'll give you kind of an outline, a broader outline for how that method goes once we have applied it a few times. The first problem is kind of the easiest form of the trig substitution, and that is number 9 on page 507. So when we look at this integral, we're asked to evaluate this integral, and when we look at it, it looks like it might be an inverse trig function, maybe inverse tangent, because we've got a radical in the denominator, and under that radical we've got an x squared plus something. However, how do we get this 16 out? There are a couple ways we could do that without a trig substitution, do some really nasty algebra, but a trig substitution will let us solve this integral a lot easier. And so the way a trig substitution works is we have to use at the base, the trigonometric property sine squared x plus cosine squared x equals 1, and then variations of that for the different functions. So for this one, we've got to find a trig function that when squared plus a 1, or in this case a 16th, but we could take the 16 out by adding a 4 to the trig function that we're putting in for x. So a trig function plus 1 that equals something else. So in this case, that would be tangent. Tangent squared plus 1 is equal to secant squared. And there's proofs for that in your pre-calc book probably. If you still have that, there are definitely proofs for that in the pre-calc videos. And there are also explanations of that in your book as well. But so what we're going to do is we're going to call x that trig function. We're going to call it 4 tan theta, and we have this 4 there because that 4 squared is a 16, and we can factor that 16 out, so that we'll just get the tangent squared plus a 1. And then we're already going to do some of the work that we're going to need to later here. We're going to get dx, so we're going to take the derivative of this. That is 4 secant squared theta d theta. And you can put anything in the argument for these functions. Like that could be a u, that could be a v, that could be whatever you want. I'm just using theta arbitrarily because it's a trigonometric function, and theta is kind of the standard variable. So we're going to make that substitution, and we're going to get 4 secant squared theta d theta for the dx, and underneath we're going to get 16 tangent squared theta plus 16. And so that will turn into and then we're going to factor out the 16, and we're going to get tangent squared theta plus 1 is equal to secant squared theta. So we're going to get root 16 secant squared theta. And then we can reduce that to, in the denominator, 4 secant theta. And so we get some really nice cancellations here. and that will make the integral a lot easier to solve. Now the integral just reduces down to the integral of secant theta d theta, and based on that new integration rule, this becomes the natural log of the absolute value of secant theta plus tangent theta plus c. And so now we've got an answer in terms of theta, but we need to bring it back in terms of x, in terms of the original variable. And how do we do that? Well, we can actually use properties of trigonometric functions with regards to a triangle to solve this, and let's do that on the next page. So remember that our initial substitution was x equals 4 tangent theta. So that means that x over 4 equals tangent theta. Now let's draw this out on a right triangle right here, with theta being there. So tangent is actually, that's sine over cosine. So the x corresponds to the opposite side, the 4 corresponds to the adjacent side of the angle, and that means the hypotenuse is x squared plus 16. So that means when we can just directly find these functions in terms of x using this triangle and using kind of the definition of trigonometric functions. So secant theta is 1 over cosine theta. So that means we're going to take the hypotenuse with respect to this angle over the adjacent side. So that is going to then be root x squared plus 16 over 4. And tangent is opposite over adjacent, so that will be x over 4 plus c. And remember that plus c. So that is broadly, and kind of in the most basic form, the method of a trig substitution. One of the variables in the integral, you call it some trig function that will make the integral all reduced down, and then you use the property of the trig functions with respect to a right triangle, kind of visually, to make those kind of reverse the substitution once you get your answer. So let's do another slightly more complicated version of a trig substitution. So now we're going to do problem 12, also on page 507, and this problem is just a little bit more complicated because we've got a variable outside of the radical. But for the most part, we're going to take this problem mostly the same as we took the last problem. So first off, we have to ask ourselves, alright, we can deal with the 5. Let's imagine that that's a 1. What is 1 minus the square of a trig function, and what would that trig function be in order for that to be one of our properties? And we can say, oh, well, it's either cosine or sine. Well, sine's a little bit easier because its derivative doesn't have a negative in it. You could technically use cosine, but sine's better because the derivative of sine is cosine. There's no negative there. So let's make the substitution. U equals, and we're going to have to take care of this 5. And since 5 isn't a perfect square, we're going to have to just use square root 5, because then once that's squared, that'll turn into a 5. Sine theta, and we're going to do the derivative work already, so du is going to be equal to root 5 cosine theta d theta. So everywhere we see a u, including outside of the radical, we're going to have to substitute in root 5 sine theta. So the du is going to be root 5 cosine theta d theta. The u is going to be root 5 sine theta, and then this the u squared is going to be 5 sine squared theta. So we can take this 5 out, and that'll make it 1 minus sine squared theta, all that under the radical. And then we can reduce this. That root 1 minus sine squared theta turns into a root cosine squared theta, which then just turns into a cosine. And so now we can do some canceling. We can cancel out these root 5s, we can cancel out these cosine thetas, and then we get something a lot nicer. We will get d theta over root 5 sine theta. And so we can express that as the integral, and we'll take out that little coefficient, the 1 over root 5, and we're going to get cosecant theta d theta. And we have an integration formula for this. So let's go over to the next page and write that out. So we're going to get, So we have 1 over root 5, the integral of cosecant theta d theta, and that is equal to 1 over root 5, but we have a negative in there for the co, and that will be the natural log of cosecant theta plus cotangent theta plus c. Now what we have to do is we have to get rid of the theta and put this all back in terms of u. So remember, the substitution we made was u equals root 5 sine theta. So that means u over root 5 is equal to sine theta. And if we think of sine theta in terms of a right triangle, and we say, okay, sine theta is opposite over hypotenuse, the opposite is going to be the u, and the hypotenuse is going to be the root 5. And so this edge right here, the adjacent, is going to be root 5 squared, so just 5, minus u squared. So if we come down here, we're going to keep that negative 1 over root 5 and the natural log, and then when we see cosecant is just the inverse of sine. So, or it's going to be, sorry, not the inverse, 1 over sine theta. So that means it's going to be the hypotenuse over the opposite. So that will be root 5 over u plus, and then cotangent is adjacent over opposite. So that is going to be root 5 minus u squared over u plus c. And that is that problem. We're going to go on now to the last, most difficult form of trig substitution problems, because you're also going to have to throw a u substitution in the middle, even after doing the trig substitution. Alright, so now we're going to do problem 18 on page 507, and we're asked to evaluate this integral here where a and b are both constants. So what we're going to have to do is we're going to have to find a way of putting the b into this part of the expression here and then get rid of the a. So already we know that we're going to have to, and we know that we're going to have to do a trig substitution here. Already we're going to have to, since we have to get rid of that a, we're going to have something over a, and we're going to have that b because we want to end up having a b squared that we can factor out, and then have some trig function squared minus 1. And that trig function squared minus 1 that we can apply our trig properties to is going to be secant theta. So we're going to have a b up here, so we get that b squared times secant theta. Now we can do the derivative work. Dx is going to be equal to b over a. The derivative of secant is secant tangent d theta. Now we'll substitute in. We will get b over a secant theta tangent theta d theta over, this is going to be b squared secant squared theta minus b squared, because those a's go away, and then all of this is going to be to the 3/2. Now we can factor out this b squared. Secant squared theta minus 1 is equal to tangent squared theta. So all of this is going to become the same numerator as before, but then b squared times tangent squared theta to the 3/2. Now we can get rid of this 3/2 because if we can multiply this exponent by that exponent, and the 2's will go away, and we'll just get cubes in the denominator. So presto, we've got these cubes in the denominator. Now we've got a b up here, we've got b's down here, we've got a tangent up here, we've got tangents down here, and so we're going to be able to do a whole mess of canceling. And so this a we can put in the denominator, this b goes away, and that 3 becomes a 2. So we're going to put our d theta over there. B squared. This tangent goes away, that 3 becomes a 2, and we'll get tangent squared, and that this a, as I said, comes to the denominator, and then we'll just have a secant theta up here. Now remember, tangent and secant can both be put in terms of sines and cosines, and unless you know off by heart what secant theta over tangent squared theta is, that's what we're going to do so that we can get some more canceling done. So let's do that over on the other screen. So we've got secant theta is 1 over cosine, and we've got our AB squared, and tangent is sine over cosine, so we'll get sine squared theta over cosine squared theta. We've got our d theta there, and now we can do some canceling. So this cosine is going to cancel with one of these cosines, and we'll just get a cosine up top when we flip this fraction. So we're going to get a cosine theta d theta, and that sine squared theta is going to stay in the bottom, and we will get AB squared sine squared theta down here. Now, how are we going to go about... Now, we can't cancel anymore. We have canceled out to the max. However, this looks like an integral that we could do a u substitution with, because the derivative of sine is cosine. We've got a cosine in the top, we've got a sine squared in the bottom. It looks like this all should work out. So we're going to call u sine theta, we're going to call du cosine theta d theta. So we put all this, actually, let's take that AB squared out just to make the integral look simpler. Take that out as a coefficient. We're going to get du, and then in the bottom we are going to get u squared. And now we can think about this as u to the negative 2 du, and then we're going to just be able to apply the very simple integration rule. So that'll be AB, and so we add, so this negative 2 will become a negative 1. We put the negative out here, and this will be u to the negative 1 plus c. So now we're going to need to do two things. We're going to need to put this in terms of theta, and then once it's in theta, we're going to need to put it back in terms of x. So let's do that on the next screen, and I'm going to write out what all our substitutions were. Alright, so since u is sine theta, that's a pretty easy substitution to make. We'll get negative 1 ab squared sine theta plus c. Now, x is equal to b over a secant theta. And so we're going to be able, we're going to do the thing with the triangle again. We're going to get ax over b is equal to secant theta. And secant is 1 over cosine, so cosine theta is going to equal b over ax. So when we think about this in terms of our right triangle, we've got theta here. Cosine is adjacent over hypotenuse. We're going to get the b down here, the ax over here, and this is going to be root ax squared minus b squared. So, since sine is opposite over hypotenuse, we can make that substitution relatively easily. So that opposite is going to be root ax squared minus b squared over ax plus c. And we can simplify this. We can cancel out these a's, and we can bring the x up. So the x goes into the numerator, get b squared ax squared minus b squared, all that under the radical, plus c. And there you go. That is the hardest kind of trig substitution you're gonna have to do in this class. So that's trig substitutions. This is one more advanced integration technique. Stay tuned for a couple more for the rest of chapter 7. It's going to be a really helpful chapter. Thanks.